So it's somewhat misleading to think of differential equations where you'll have an equation and just be able to find a solution formula nicely. For some cases, this is easy enough. For example, if you had a differential, whoa, that was much larger than I wanted. If you have a differential equation that was, let's say, dy dx is equal to 3y, in this case, we can come up with a solution formula. You can either use separation of variables or you can reason it through. Either way, you're going to come up with y is equal to c e to the 3x, where c depends on the initial value. Now, that gives us an explicit formula. If we, let's say, pick an initial value, which I'm going to put in magenta for a particular reason. Let's say y of 1 is equal to 2. And we want to look at this curve, which I will, let's say, color in green. We can graph this like so. If the bottom axis is our x-axis and the vertical axis is our y-axis, then we would have one point, let's say the point 1, 2. Maybe I'll draw there. And then we have this curve that, and let's see, goes through this. And let me just think for a second. Actually, it doesn't really matter putting the exact value, but it'll look something like so. And this would be the curve. Y is equal to, and I got to think for a second, 2 is equal to c e to the 3. So this would be 2 e to the negative 3 times e to the 3x. We could actually find the c value based on this initial value. So we get this curve. Now we do this type of thing repeatedly throughout the course, and we look at differential equations, say, what is a method that we can apply to this differential equation and actually, or this initial value formula, and get a solution curve like this. Now it's nice when we get a solution curve or solution formula, but what happens when we have a differential equation that looks something like this? Y triple prime to the 4th power plus cosine of y is equal to e to the x to the y to the x squared, or something just ridiculous. In a case like this, it is not reasonable to hope to find a solution formula. That's essentially too much to ask. And this is maybe a little bit of a more extreme or dramatic example, but even with some relatively simple differential equations, such as in some cases, or a lot of cases, second order diff eqs. There's many second order differential equations where it's either too hard to find a solution formula, like it would just be too much work, or we don't know. Maybe there is one and it should in theory be possible to find it, but we just don't know how to do it yet, or the process would just be agonizing. Or it can be, well, I guess that's just it. It's either too hard or one doesn't exist. There may just not even be one at all. So in the case that a solution formula is either too hard to find or doesn't exist, you're left kind of wondering, well, what do we do there? So what if a solution formula is too hard to find or doesn't exist? And if you look at all the possible differential equations there are, most of them will be in this category where it is too hard to find a solution formula, or that solution formula doesn't exist. So what then? Well, we want some other way to get an idea of what the solution would look like if we did have a formula. And that's where numerical methods comes into play. So the idea is this with numerical methods in general. So There are lots of different numerical methods, but every one of them operate under the same principles here. The principles are that you have some starting value, which I'm also going to draw in magenta here. So let's say there's again a y of 1 is equal to 2, and I'll put that magenta. So you have some starting point wherever, say like this. And what you do is you apply a numerical method to now approximate successive values. So you've got your starting value. It's at 1, 2, but it can be wherever. You then will go through a process, and I'll say it in generality because this is standing in for all the different processes that you could use, all the different methods. You blah, 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 go through some algorithm. So there's an algorithm that allows you to approximate a new point. And maybe I'll put that new point in green here. So we go through, we do an algorithm, we get a new point. Then maybe we blah, 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 do the algorithm again. And we get to yet another point. And you just repeat this algorithm over and over until you have as many points as you would like. And there's a few things to notice. One, with solution formulas, we get these usually continuous functions, or at least piecewise continuous on pieces or on set intervals. So we have continuous in this case. You know the y value, or we know the y value for any x value within, this certain continuous interval. With numerical methods, it's discrete in the sense that we only have it for a few points picked out here. Like we have it for 1, and I don't know, maybe this is at 2 and this is at 3 and so on. But we don't fill in this whole interval. We don't know, for instance, or have an approximation for the y value at this point. We're just not sure. So there's continuous versus discrete. Continuous is better because it just gives you more information, a clear picture of what's going on. Discrete is not as good as far as information returned, but it is good in the sense of being reasonable to compute. You only, let's say over this given interval here, if these are the same intervals, we compute uncountably infinite number of points, or we compute 3 points. There's just a massive difference. So there's some advantage to having a continuous curve. It's more information, but coming up with that curve, if we didn't have a nice solution formula, it would just be computationally too much. So discrete has the advantage that it's computationally accessible. But there's also less information. The other thing is to keep in mind that we are talking about approximations for these points. So the magenta point is special in the fact that it is surely on the solution curve that passes through this point, because by definition it passes through this point. But after that, it may be that the actual solution curve might kind of look like that or something. It may be the yellow. So that the green points are just trying to be close to the curve, but they're not going to be exact. They're just approximations. Whereas on this curve, the curve is exact over on here for the solution formula. So that's some of the differences between solution formulas and numerical methods. But if it at all seems like numerical methods aren't that great, they're actually wonderful, because most of the time you're going to encounter a differential equation, an initial value problem, and you're not going to, actually, I guess there's more information here because it's higher order, but you get the idea. Most of the time there's not going to be a solution formula, so numerical methods are sort of the best hope we have of getting some information. And as I mentioned earlier, there are many different types of numerical methods. We will look at one for sure today, maybe a second. And then I think there's going to be an extra credit homework that gives you yet a third. But there's many of them. And people are constantly trying to come up with ones that are more accurate, computationally less expensive, and things like this. Have better error bounds, and they're always trying to refine them and improve them. So that is definitely a big area of mathematics, is numerical methods for differential equations. As I mentioned, we'll look at one in particular today for sure, but once you get the idea what's going on with this one, you really got the idea for all of them. The specific algorithms will be different per numerical method. That changes between the numerical methods, but the idea remains the same. It's always a case of applying an algorithm to get from a start point to your first approximated point, and then applying the algorithm again to get to your next approximated point, and then just repeating that over and over. So once you understand the algorithm, it's just a matter of repetition. And once you set up the algorithm, depending on whether you're using Excel or using R, the programming language for data science and so on, whether you're using Excel or R, it's just a matter of reiterating that algorithm. So if we can understand this algorithm, everything else, as far as using that numerical method, is easy. So I'm going to focus today on really putting in time to understand the algorithm process period, and then specifically for the numerical method called Euler's method. So that's what we'll focus on. So let's go ahead and do it. Okay, so Euler's method, what's going on with that? Well, let's say, let me do this in generality, and then we'll look at a specific case. So say we have dy dx is equal to f of xy. One thing you'll notice is this does have the form to give us a slope field, so we can compute a slope field from this, which is important. And we're going to also have, besides this, an initial value, which I'll just say y of a is equal to b. I'm going to color these in different colors to try to make it easier to follow and just organize this in your mind. Let's color this initial point. Let's color this magenta. And then I'm going to color this thing cyan. And, whatever the colors are, it's going to be to make it easier to track shortly. Now, as far as what we're doing geometrically, so maybe I'll put over here the geometry, and then on the left, we'll do the computations. So if here's our y-axis, here is our x-axis. What we're going to do is we're going to start out at some point AB. We're going to look at that point, and it's highlighted in magenta to emphasize that it is a particularly important point. It's where we start out, and it's a point that we know for sure is on the curve, because by definition, we want to find the solution curve or an approximation for that curve that passes through this point. So, I mean, just by definition, it has to be exact. Now, with that, maybe I'll move this over a bit. We now want to look at the algorithm for Euler's method. First, well, let's think for a second. We want to come up with another point here, somewhere. It's wherever. What are the characteristics of that point? Well, that point has an x value and it has a y value. So we need to find two things. We need to find x values and y values. The x values are are just straightforward. I'll just say it. And then the y values require a little more care, but in some sense, it's not that much different than the x values. It'll seem more involved, but once you sort of absorb it and take a look at it, you're like, okay, yeah, it's really just the same as the x values with one slight tweak. But let's start with the x values. what we want to do is to, in some sense, cast a net over the x-axis. And when I say cast a net, what we're going to do is we're going to choose a step. Where should I put this? I'll put this here. Nope. We're going to say step. And just because I'm compulsive, I want to write that a little nicer. Step H. Now this H is going to be like literally, or not literally, but figuratively, how much we step to the right as we're doing new approximations. So if we start at A, we quote unquote step over by an amount H until we get to this new point, which is A plus H. And just like with walking, we presume that we're going to take sort of even steps, or equally paced steps. So then we go over again by H. And actually, just for the sake of making it easier when we add everything else to this, I'm going to visually enlarge in the H. I'll move this. So I want to give us enough room, but also, yeah, there we go. So that gives us A plus H. Then we would keep doing it. So we'd move over by the same amount again to, let's say, here. And then we have A plus H. And so on and so forth. We just keep not single H, 2H. So we keep moving over by H each time. Now from there, one way I like to think about it is that we're going to use the slope here, dy dx, to be able to figure out what the new value is going to be. So imagine we look at that curve. So we take the slope and we follow this up. I call it a curve, but you can call it a line or what have you. We follow this up like this. So let's say this is the slope. And this slope, which is dy dx, should I maybe write that a little nicer? That's going to be equal to f, just by definition, because dy dx is equal to this formula, or is given by this formula. And in particular, we're going to be looking at the point A, B. So at the point AB, if you plug that into the function, you get a value, and that gives you the slope. So that gives you this cyan line here. Now what we like to do is find a point, the new approximated point that has an x value and a y value. So let me maybe write that. So the new approximated point should have two things. Should have an x value and a y value. The x value, we know it's going to be this value here. So it's going to be A plus H. So we have A plus the value H. Now we need to know what the y value is, and then we'll have our approximated point. Graphically, this is kind of nice to see. We want to think about where would the y value be? Well, the y value is going to be above A plus H. And okay, that's curved enough that it's going to drive me nuts. Let's instead, I know, let's do a darker line so it's not so obtrusive. Yeah, let's go like that. But straight. Okay, good. So if our x value is A plus H, the y value is going to be above that. And then we can see that it intersects the slope line here. So that's going to be where we have our new point. We already know the x value of our new point, but we don't know what the y value is. However, just looking at the geometry, we can find this out, and it's not too bad. In particular, maybe I'll use this sort of dark gray again, so we can follow, but it's not so distracting. So we'll notice that we have this right triangle here. This right triangle has dimensions. Well, it has dy dx for the hypotenuse. That's fine. Then it has a base of course, h. And then now the only thing left is to find out what is this height here, or this change in height, if you will. What's this side of the right triangle? And now we can do a computation to the side where we notice that the rise over the run, that's the same thing as dy dx, which is the same thing as f at this given point. So this should maybe be rise over run at the point AB. So that's worth highlighting. All these are at the point AB. So let me actually maybe give this a little bit of a heading. So this is specifically at the point, and again, to make it a little easier to follow, let's do it like this, at the point AB. We have that the rise over the run is equal to dy dx, which is equal to f of, and now that f of is going to be the f of AB of a particular point. All right, well, are we closer to where we want to be? I claim, yeah, we're getting there. One last part of the equality is to say, well, this over here in the triangle is the rise, and then the run is just going to be h. So we have the rise over h. And now we say, well, what is it going to take to find the rise? Well, just a little bit of algebra will give us, and let me move some of this up just so we have more room. We find that the rise is going to be equal to h times f of AB. And I'm belaboring this to hopefully make it easier later, but let me color in AB. Let's color in H. That'll be yellow. And let's see, let's also color in this slope here. And since we're doing that, let's also get this. Okay, good. So we're tracking colors nicely. Now, in order to find the new y value for this approximated point, and I'll highlight that this is going to be our green point, and I will move this around a little bit just to make it easier to differentiate between different things. Now I'll put some dividing lines again just to make it a little nicer. So our new approximated point, we found the x value, and now the y value is going to be, well, we'll notice here that it's going to be b plus however much the rise is. So we start with b, and then we add to it the rise. The rise we found to be exactly this down here. So maybe what I'll even do is just copy that. Make sure it fits. All right. So now we know what the coordinates of the new point are. And again, it's highlighted in color, hopefully to make it easier to follow what's going on. Well, notice that what we did is we started with the point AB. Then we used h to get the new x value by adding h to it. And we used h along with the slope to get the new y value. But in both cases, we take the current value, AB, and then we use h along with h times the slope to get to the new, like to one, move over a certain amount, and then rise up a certain amount and get to our new point. This is Euler's method. This is the algorithm to go through it one time. If we wanted to find more points, what we would do is we would then go ahead and repeat this algorithm just over and over, however long we want it to. And there are tools like Excel or R, I think would work nicely too, where you can, once you set up the process, you can easily iterate it through and it goes very quickly. So this is where a lot of the work comes in. And, you know, I've taught this class many times, and I've noticed that students who understand this, like the concept here, can breeze through the Excel sheets and all the computations. But when there's any confusion about what's happening in these steps, setting up the Excel sheets can be really difficult. So hopefully this gives a decent idea of what's going on. I'm not expecting it to be 100% clear or expecting you to be a master. I'm not putting pressure on you in that sense. I'm just saying it's worth spending the time, if you're not sure, to really understand this process, because it will then make everything else much, much easier. And I see that I have a frozen screen for some reason. So I am going to, actually, it's a good time to switch anyways. I'm going to stop sharing this screen, and then we're going to look at an Excel, or actually LibreOffice. So I'm changing this, and now let's look at LibreOffice here. Okay. Actually, I wonder if I can do both at the same time. No, I don't think so. Okay. Yeah, I was hoping to, excuse me, have a picture up of Euler's method, like what we just drew, but excuse me, it looks like I can't do the iPad screen and this at the same time. So let's just give this our best effort. Let's say what we want to do is look at the differential equation dy dx is equal to 2x minus y. I'm going to right away color that in a cyan, well, it's, I guess, more blue than cyan, but in this color, approximate to what we just saw. This will be our slope. It's also the differential equation we want to approximate points for. And then we're going to have a starting point. This, where am I getting this diffie-q from? It's what's in the lab. So going through it, we can kind of check our work based on what is presented there. But there will be other differential equations you'll do this for. The starting value it gives us, or starting point, is y of 0 is equal to 1. I'm going to color that in magenta to represent that that's our starting point, to keep track of it. It's also an exact point. Now, let's also change, or while we're at it, actually I like this. Let's do this. Let's say that the h, because of the way we actually want to access this, I'll actually move h here and give that fill. Okay. Let's set h equal to 0.1. It's what's given in the lab, so that's why I'm picking that, but we can change the values. All right, so these are essentially our ingredients that we'll use to build approximations. Now, as I mentioned, there's going to be a x column. And we're going to start off at the point x is equal to 0. And I'm going to highlight that in this magenta to stress that we're given that by this here. So our starting point is 0, 1, 0 for x, 1 for y. So that's why I picked that. We're also going to have a y column, and that y is going to be 1 as well, for the same reason that it's just the starting point we have here, 0, 1. So they're in magenta, like this is a magenta because it's giving us the same information. And what we can do right away is say, well, we can compute the x values. Like what we want is to get a bunch of points, which is a bunch of pairs of x and y values. And I just realized I should check chat really quick. Okay, we're good there. If someone with a microphone sees someone say something in chat and I'm ignoring it, feel free to interrupt and let me know so I don't let that question go. But we've got this point, and what we like is more points. In each case, it's going to be pair x, y. We can actually compute the x values easily enough using Excel by saying, all right, the next x value is going to be whatever the previous one was. So I'll select the previous cell, which is D4. Then what we're going to do is we're going to step over an amount, which is going to be exactly this cell. This is the step. But the way it'll work with copying and pasting these formulas is we don't want the cell that we reference for the step to ever change from B3. As we copy the formulas, it's helpful that the formulas adjust by column and by row so that you can copy a formula down and adjust the rows so you don't have to redo the formula every time. Without that feature, I don't know that Excel would actually be very useful. So that's a critical thing. However, there are some points where you don't want the cell to change as you change your formula. To indicate that you don't want the reference cell to change, even as you copy into new cells, you don't want the column or the row reference to change, you put $signs around the column identifier. So we say $B $. So now, okay, 0.1, that's fine. 0 plus 0.1 is 0.1. But now notice when I Control C copy this cell, I move down and now I'm going to Control V paste. So Control C. Let's copy. Control V is paste. That'll make this a million times easier. It's also better than the click and drag method, in my opinion, for a few reasons. So we copied it down. Now, what I want to highlight here is that notice with the D5 cell, we've got D4 plus B3, or fixed B3. Now, notice when I go down to D6, when I go below, it's D5 plus B3. The B3 reference doesn't change. So it's D4 plus B3, D5 plus B3. We don't want that reference to change. That's good because we're always going back to this same cell. Whereas here with these formulas, when we copy the formula down, it works as intended, where the formula says take the last value, which is 0.1, and then add the step to it. We don't want to go back to 0 and then add the step because that would just give us 0.1 again. And now that we're maybe feeling comfortable that this is working, we can Control C to copy this cell. And then we're going to hold Shift and move the arrow keys down. And then now Control V for paste. Now we have all these x values. And it's worth noting now, because this will come up later, that because we've chosen to organize it this way, if we now change this cell, it should change all the cells that involve this formula. So if we go instead of 0.1, if we go to, let's say, 1, it's now going to go like so. Or if we go to 0.05, it's going to it's going to increment by 0.05 each time. Okay, so that's good. Let's go back to 0.1 just for base reference. Now we want to know what are the y values going to be. We've got the x values, that's great. But what are the y values? If we think back to how we got the y values and the x values were just the previous one plus the step. Okay, well, that's fine. But with the y values, it was similar with a little bit of a difference. The similarity was it's going to be equal to, and don't enter this, I'm just showing you as an example. It's going to be equal to the previous one plus, and I'm going to write in something. That something was going to be h, the step, times the slope. And you'll notice we haven't referenced the slope at all, so probably it's a good time to do it now, and we have to do it now if we want to get the new y value. So it's E4 plus something. It's the last one plus a new thing. And this new thing is pretty much what is different between all the different methods. It's always, what is the formula you use to get the new y value? For us, it's going to be this. We're going to say, actually, I'm just going to copy the cell. We're going to use this, which is the slope, which I'll, again, to really try to reinforce this, color it blue again. Now this value is, actually, might as well do the whole thing. This value is going to be equal to 2x minus y. So as a formula, we're going to say 2 times x. X, in this case, is going to be the cell D4. Why? Well, it's under the x heading. These are the x values. Then we're going to subtract from that the corresponding y value. So we're going to subtract E4. Now we hit enter, and we get -1. So that is our slope at the point 0, 1. So to really highlight this, what's going on, this is the slope at the point 0, 1. That's what this thing is. Now we're going to use this slope to come up with the new y value. I said this was E4 plus something. The something is going to be this. It's going to be the step times the slope. So it's going to be the step, which again, we don't want that to change ever. Or we don't want the reference to the cell to change ever. So that's B3. And then we're going to multiply that step, which is the B3 cell. We're going to multiply that by this thing, which is F4, the slope. So it's the step times the slope, which, let me say a few more times just to really drill it home. It's the step times the slope. With x, we just added the step. With y, we add the step times the slope. So it's x is just the step, y is the step times the slope. Now if we hit enter, we get 0.9. And that's good. Now actually at this point, we've gone through the algorithm one time, and at this point it's kind of easy to clean it up. We just say, let's copy this slope formula down. And now notice it's going to take 2 times D5 minus E5. So it's going to sort of like the formula is going to shift to the new row, which is actually what we want. And let me maybe go back here to say that this is our approximated point, or at least, do I want to do that? Yeah, I'll do it in green to keep it consistent with what we've done previously. Okay, now I'm going to take these 3 cells. You could just take the E and F columns, that would work too, but either way, I think for the sake of color, I'm going to continue it like this. And we're going to just copy this down. That's probably farther than I needed, but it doesn't matter. So like so. And this, let me put like this. Okay, good. All right, so what did we do? We started with a magenta initial point, and then we used the slope and the step to compute the new x and y values, and we get these here. Now, one thing you'll be asked to do, and let me check chat. Okay, looks good. The one thing you'll be asked to do is to find, so as part of the lab questions, you would be asked to find y of 2. Y of 2 means what is the y value when x is 2? And if we look here, here it is. When y is equal to 2, we have 2.364 blah, blah, blah. So we'd say y of 2 is equal to, so I'll move that over. It's going to be equal to just this value. So y of 2 is equal to this 2.36 blah, blah, blah. For the lab write-up, what you would do is that when it asks for this differential equation, when we have a step size of 0.1, what is y of 2? You'd say, okay, well, y of 2 is equal to this. You don't have to fill in all these tables or provide a copy of your Excel sheet. You just have to say, what did you get for this value? And then it will also say that if you change the step size, what is y of 2? Now notice if I cut the step size in half, I go 0.05. I no longer have the right rows here because now it's saying x is equal to 1. So it won't be this. Instead, we have to go down because we go through more steps. A step size is smaller, means we travel less distance, take more steps in between. So y of 2 is now going to be equal to whatever this is here, this 2.38, which I think is relatively similar, but either way. So we get this value. So it depends on what your step size is. As you change your step size, your 2 will be in a different row, and then, but you still just want to find out what the y value is there. All right, good. So that is that. There is another thing that we want to talk about, at least for this Euler's method. It looks like we won't get to improved Euler's method, but there's an explanation how to do it, and we can talk about it in recitation maybe on Thursday, or you're going to be welcome to, ask me. I've got a bunch of office hours and help session tomorrow, but let's finish up at least for Euler's method, how this would work or what we'd want to talk about. The other thing we would want to talk about, besides what is y of 2 or y of whatever, is the comparison. Actually, I'm going to change this back to 0.1. A comparison between what is an approximate y. So I'm going to put approximate y. And to highlight that that's what we're looking at now, approximate y. And then let's look at an exact y. Now, I said earlier that you would use a numerical method when you couldn't find out the exact values. And that's true. So why are we talking about exact y now? We're talking about it because the point of this is not to apply a numerical method to some differential equation that we can't necessarily find a solution formula for. It's just to practice doing numerical methods, just to get to practice. With the exact y, what we can do is we can compare the approximate and see how close they are. In the field, when you use these, what you'll have are some bounds on the error where you can say, I know I'm within a certain range of the actual, using some methods. But here we can actually just compute what the exact y is. Now, this is a first order differential equation. dy dx is equal to 2x minus y. That's first order. It's also linear. So first order linear, you can use integrating factor. If you do, what it ends up being is it's actually in the lab here, is the exact y is equal to 3 times the exponential negative x plus 2x minus 2. Where do you get that? You get that from doing integrating factor or using another method like Laplace transform on this differential equation. So you use the methods that we have learned / will learn to come up with this formula. Now, if we say that y here is equal to 3 times the exponential negative x is again the D4 cell, plus 2 times x is again the D4 cell, minus 2, unsurprisingly, we get 1 here. But now, if we take this formula, Control-C, copy, and then hold Shift with the arrows, we'll let you select through or highlight multiple. Control-V for paste, and we get these values. Now, it would be interesting to compare the approximate y versus the exact y. So let's do that really quick. What we want to do is what's called the relative error, where we take the difference between the two. So here we have a formula, and the formula is take the difference from the exact y and the approximate y. So that's the difference of these cells. And the reason it's called relative or percentage error or proportional error is that we're going to divide by the exact. So we're going to see how much is the difference compared to what the values actually are. And it should be 0 to start with. That's good. But then if we, let's say, paste down a few, we'll notice we're getting these numbers. And then let's format and change to percentage. Good, we get that. And let's take Control-V to copy, Shift plus directional arrows to highlight, and Control-V, or maybe I said Control-V, but Control-C to copy, Control-V to paste, and we get these. So what you would say when the step size is 0.1, when x is equal to 2, is you would have, let's say, an error of 1.72. Now notice if you change the step size, 0.05, now you look at y is equal to 2, you have a different percentage error, 0.85. So those are the main types of questions you'll be asked, is how does the percentage error or relative error change? And what is the actual value y of 2? All right, I think that's what I've got for you. So you're welcome to stick around and ask a question or two. Otherwise, you have a good day. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.